Hello everyone, welcome back. Today's video is going to be an introduction to two operations that we do with three-dimensional vector fields, curl and divergence. Alright, here we go. I'm going to start with a bit of a review here. A while back we talked about the curl of a two-dimensional vector field, which remember was a function, right? At every point we evaluate this difference of partial derivatives of the component functions of a vector field, qx minus py, and this is a function that tells us at every point in the domain of the vector field how much the vector field is rotating counterclockwise. This would be a positive number if the vector field were rotating counterclockwise, negative if the vector field is rotating clockwise, and 0 if it's not rotating at all. And we saw already that there is a connection between the curl of a two-dimensional vector field and line integrals around loops in the form of Green's theorem. So what we're going to do today is take this idea and extend it to three-dimensional vector fields. So the question we're going to ask is, if we have a three-dimensional vector field, how do we measure the degree to which it's rotating? And what does that even mean for three-dimensional vector fields? Well, here's an example. This is the vector field f of xyz equals negative z, 0, x. And before we answer this question, I actually want to take a look at this vector field in GeoGebra to see what we even mean by rotation when we're talking about three-dimensional vector fields. So here's the vector field negative z, 0, x. And you can kind of see as I'm moving it here, it looks like it's rotating. It looks like it's actually rotating around this y-axis here. The green axis is the y-axis. And that way that I just phrased that as saying that the vector field is rotating around an axis, it turns out that any kind of rotation in three dimensions always has an axis. So whereas two-dimensional curl was a number measuring how much a vector field was rotating counterclockwise, the three-dimensional curl of a three-dimensional vector field is going to be a vector, because we need to specify not only how much the vector field is rotating, but also in which direction. And for this direction, the direction that the curl is going to point in will be the direction around which the vector field is rotating counterclockwise. What I mean by that is, if I take this vector field and move our perspective so that we're looking at it from the point of view of the negative y-axis, it looks like it's rotating counterclockwise around the negative y-axis. So the three-dimensional curl of this vector field is going to be a vector that points in the negative y direction. So again, here's that key idea. Rotation in three dimensions always involves an axis. So the three-dimensional curl of a three-dimensional vector field is going to be a vector that points in the direction of the axis of rotation of the vector field at each point. All right, so that's the intuition. Here's how we actually compute three-dimensional curl. The notation for it is just written curl of f. We don't put a 3 as a subscript. It's sort of implicit if we write curl that we're talking about three-dimensional curl. If we want to talk about two-dimensional curl, we need to put a 2 subscript. So, like I said, the three-dimensional curl of a vector field is going to be a vector field itself. And just like two-dimensional curl, it's going to be a combination of the partial derivatives of the component functions of this vector field. But it's a little bit more involved. So what we're going to do is we're going to take the z component and differentiate that with respect to y, and subtract from that the y component differentiated with respect to z. And that'll be the x component of the curl. For the y component of the curl, we'll take the x component and differentiate that with respect to z, and then subtract the z component differentiated with respect to x. And finally, for the z component of the curl, we're going to take the y component and differentiate that with respect to x, and subtract from that the x component of the vector field differentiated with respect to y. And you actually might recognize this last part. Qx minus py is two-dimensional curl. And actually, all three of the components sort of have the same form, where we're taking the derivative of a component with respect to a variable minus the derivative of another component with respect to a different variable. And there's kind of like a switching going on in the sense that q is the y component and we're differentiating with respect to x, and p is the x component, we're differentiating with respect to y. The same thing is going on in here for the y and z components here, and for the x and z components here. So again, this is a vector at every point in the domain of the vector field f that is going to tell us the axis of rotation of the vector field f at that point. And maybe a picture to have in your head for this is that if this is the point p, then if the curl of f points in this direction at p, which we might write this way notationally, the curl of f evaluated at p, then this vector is pointing in the direction around which the vector field is rotating counterclockwise, in the sense that if you imagine looking at P from the point of view of the tip of this vector, you should see the vector field rotating counterclockwise around P. So that's what curl means, and this is how to compute it. But this formula is kind of nasty, it's unpleasant, it's sort of hard to memorize. So what I'm going to show you next is another way to think of this same formula. And so here's a convenient way to remember how to compute the curl of f. You can take a cross product of this vector, where the first entry is a derivative with respect to x, the second entry is the derivative with respect to y, and the third entry is the derivative with respect to z. So this vector, which is not really a vector because its entries aren't numbers, they're kind of operators, but we're taking the cross product of that with the vector field p, q, r. So in other words, this is the vector field f, and this is a vector field of partial derivatives. So let's see an example of this. With that same vector field from before, let's compute using this formula the curl of the vector field. So to take the curl, take the cross product of this vector of partial derivatives with this vector of functions. And when we go to compute the cross product, when we're multiplying an entry from this vector with an entry from this vector, what we'll interpret that as is take the corresponding derivative of the function. So here's how I like to compute my cross products. I'll write the two vectors sort of in this table here, and then I'll repeat the first two columns. And then I'll do these kinds of crosses where I take this times that, and this times that, and then this times that, and that times that, and that times that, and that times that. Any way you compute the cross product is fine. This is just how I do it. But anyways, what I meant by that is when we're multiplying along these line segments, it means that for the first entry, we'll take the derivative with respect to y of the function x, we'll get 0. And then we'll take the derivative of the function 0 with respect to z, we'll get 0. For the y component, we'll take the derivative with respect to z of negative z, and we'll get negative 1. And then we'll take the derivative of x with respect to x and get 1, and then we'll subtract that. And for the last term, we do the same thing. The derivative of 0 with respect to x is 0. The derivative of z with respect to y is 0. So we get the vector 0, negative 2, 0. Which, remember, going back to the picture of this in GeoGebra, that's what we anticipated. Since this was a vector field for which, if we looked at it from the direction of the negative y-axis, it looked like it was rotating counterclockwise. So the curl is pointing in the direction of the negative y. But anyways, that's what I mean by this kind of cross product notation. Be careful not to overinterpret this, because this isn't a vector. It doesn't have a direction. And so we're never going to say anything like the curl is a vector that's perpendicular to these two, because this vector doesn't have a geometric interpretation. It's meant to be just a notational thing that helps us compute it. But I'll also note that sometimes an alternative notation for curl that you'll see is upside down triangle cross f, which is a reference to this means of computing it and sort of referring to this vector here as the upside down triangle. Another quick example that I'll leave actually to you to confirm, if you take this vector field x, y, z and compute its curl, you'll find that you get a vector that is 0 in every component. Maybe we would write this as like the 0 vector, so 0 with a hat on it. What that should mean is that this vector field isn't rotating. It doesn't have any rotation. And I'm going to show you what that vector field looks like in GeoGebra so we can confirm this. So here's the vector field x, y, z. It's a bunch of vectors that are pointing away from the origin at every point. And you can kind of see it doesn't really look like it's rotating. There's no rotation here. If you imagine this vector field being the flow of a fluid like water, and you submerge like a beach ball underwater, this beach ball would just kind of be pushed by the vector field, but it wouldn't be rotated anyway. Unlike that previous vector field we were looking at before, where a beach ball put into that vector field would rotate along an axis parallel to the y-axis. So that kind of explains why the curl that we computed for this vector field is 0. But actually, to transition to our next topic, it looks like this vector field has something else going on that we might want to be able to quantify, which is that this vector field looks like it's expanding away from the origin. So what we're going to move on to next is divergence of vector fields, which will be a measurement of how much a vector field is expanding like this one or contracting. So here's the qualitative definition of divergence. And again, it is going to be a measurement of how much a vector field is either expanding away from or contracting towards a point in its domain. For the mathematical definition, if we have a vector field whose entries, again, are called p, q, and r, then the divergence, which we'll abbreviate as div of f, It's going to be another combination of the partial derivatives of these component functions, like this. We'll take the partial derivative of p with respect to x, and the partial derivative of q with respect to y, and the partial derivative of r with respect to z. So again, we have the derivative of the x component with respect to x, the y component with respect to y, and the z component with respect to z, and we're adding them. And what that means is that this is actually going to be a scalar. So the divergence of a vector field is a function whose value is a number at every point. And it turns out that if at a point in the domain of f, this number is positive, then the vector field is expanding. And if it's negative, then the vector field is contracting towards the point. And lastly, if the divergence is 0, then it means that the vector field is neither expanding nor contracting. So I think the best way to see what this means is to do a couple examples. But the last thing I'll note is that if you liked the triangle cross f formulation of curl, then there's a similar one for divergence, which is we're taking this upside down triangle and we're taking the dot product of that with the vector field f, meaning we're taking that vector of partial derivatives and dotting that with f. Again, this is just a notational thing to help you remember what this formula is, and it doesn't have any geometric interpretation. For example, if the divergence of a vector field is 0, it's not saying anything about how this is perpendicular to this. So it's just a notational thing. So here are a couple examples of computing divergence. Divergence tends to be, because we can just go term by term, take a partial derivative of the x component with respect to x, the y component with respect to y, and the z component with respect to z, and then add them. If we do that for this one, all of those computations are 1, and so we get that the divergence of this vector field is a constant 3. Remember, in general, the divergence of a vector field can be a function, but what this is saying is that at every point in the domain of this vector field, it's expanding away from that point. And if we go back to the picture really quick, we can see that that's happening, and not just at the origin. If you look at a point over here, then the vector field is expanding away from this point in the sense that if you think of these as representing the flow of a fluid, into the point near where my cursor is, there's a small arrow pointing in and a larger arrow flowing out. So there's more fluid flowing into that point than there is flowing out. And that's what we really mean by saying the vector field is expanding. And for this last example, this is the vector field we were looking at earlier when we computed curl. If we take the divergence of this vector field, we take the derivative of this with respect to x and we get 0. The derivative of 0 with respect to y is 0. And the derivative of x with respect to z is 0. So this is a vector field whose divergence is 0. And if we go back to GeoGebra and look at that vector field, then maybe we can see that even though this vector field has rotation, it doesn't really expand, in the sense that if it were modeling the flow of, say, air in a room, then that air isn't expanding or contracting. Everything's sort of staying the same size as it flows through this vector field, but it's just rotating around the y-axis. Now, this isn't meant to tell you that every vector field is either something with non-zero divergence but zero curl, or is something with zero divergence but non-zero curl. You could very easily come up with a vector field that has non-zero curl and divergence. You could come up with and actually in general, a vector field will be something with non-zero curl, non-zero divergence, and actually one for which those curl and divergences are functions and not constant. But these were meant to be simple examples that showed you what's going on geometrically when you have constant positive divergence or constant zero divergence. And for curl, this one had zero curl, and this one had curl that was pointing constantly in the negative y direction. So that's where I'm going to leave this one. As always, you'll get a better sense for what curl means and what divergence means and what they represent geometrically as you're practicing while you're working in class and while you're working on the homework. In the next video, we'll see how three-dimensional curl fits into the three-dimensional version of Green's theorem. I gotta say, I'm pretty stoked about that, so I'll see you in the next one.